Hello everyone. Before the starting of my presentation, I would like to thank to the organizer, Ho Jolie, for the invitation. It is my pleasure to present some of my works in this geometric analysis festival. In this presentation, I would talk about my works of curvature estimates for minimal multiple junction surfaces and the generalized Bernstein theorem for minimal multiple junction surfaces. In my talk, I will only focus on triple junction surfaces, since the method during this case is essentially the same with the general case, and it is much more easier to understand. I will divide my talk into two parts. In the first part, I will cover some well-known basic properties about minimal surfaces, including curvature estimate and the generalized Bernstein theorem. Especially, I will help you recall the sketch proof of LP curvature estimate and how to get generalized Bernstein theorem, since this method will be applied to the case of triple junction surfaces. In the second part, I will focus on the topics related to minimal triple junction surfaces. This is the topics in the first part. It will contain some definitions on the basic properties of minimal surface, including first and second variational formula. Then we will focus on the LP curvature estimate and the generalized Bernstein theorem, including their proof. At first, let's give the definition of minimal surface in R3. Note that these definitions work for higher dimensional minimal hypersurfaces. We say a surface sigma is a minimal surface in R3 if the mean curvature vector vanishes identically. Here, the mean curvature vector is usually defined by this formula. Here, EI will be the normal coordinate around a point in sigma, and the gradient here is just the Euro gradient in R3. Actually, there are a lot of equivalent definitions for minimal surface in R3. We list two important equivalent definitions here. The first one is sigma is minimal if and only if sigma is a critical point of area function. This is because by the first variation formula, we can actually write out the first variation of area. For example, let sigma t be one parametric family of surfaces with variational vector field x, such that sigma naught equal to sigma. Then the derivative of area is given by this formula. You can see that this integration is equal to 0 for any x if and only if the mean curvature vanishes identically. The second one is sigma is minimal if and only if the coordinate function is harmonic on surface. Note that the Laplace operator here is the Laplacian-Beltrami operator on surface. This is because we can compute the mean curvature vector by taking the Laplacian over position vector. So we can see that mean curvature vector H sigma vanishes if and only if the coordinate function is harmonic. After giving the definition of minimal surface, let's see some examples of classical minimal surface in R3. The first one is the standard cardinoid. The equation for cardinoid is given by this formula. It is a rotational symmetric minimal surface in R3. The second one is the helicoid type minimal surface. The left image is a standard helicoid and it's given by this formula. The right image is called a band helicoid. It can be computed by Bernoulli's formula, given analytical curve Ct. For example, like this circle here, and any analytic prescribed normal vector field NT spinning around this circle. Then, using Bernoulli's formula, we can find a minimal surface pass through this circle with normal vector field given by NT along this curve. These two types of minimal surface is quite important in classification of minimal surfaces in R3 according to the results due to coding manicosis. They can be viewed as a local model of minimal surface with sufficient large curvature. Keep in mind these examples because we will use these examples to construct the minimal triple junction surfaces. Now let's talk about the second variation formula and stability of minimal surfaces. Let sigma be a minimal surface in R3. For any variation sigma t of sigma variation with the variational vector field x, we can calculate the second derivative of area and get this formula here. The function phi is just the inner product of x and the normal vector field nu. As usual, we say a minimal surface sigma is stable if the second derivative of area is not less than 0 for any variation. So if a minimal surface is stable, we have stability inequality in this form. Basically, it says the L2 norm of second fundamental form can be controlled by the L2 norm of gradient of a test function. For stable minimal surfaces, we list several curvature estimates as following. The first one is due to Hahn. Hahn showed that one can get curvature estimate for minimal graphs. Note that minimal graphs is a special case of stable minimal surfaces. This curvature estimate roughly says if the minimal graph is defined in disk dr with radius r, the norm square of second fundamental form at the center of disk can be controlled by c over r squared. Moreover, so Simon Yao gave the LP estimate of curvature. It works for higher dimensional minimal hypersurfaces. Let sigma be a minimal hypersurface in Rn which is two-sided stable. Then for suitable P and C1 phi, we have the following inequalities. Basically, we can control the L2P norm of second fundamental form by the gradient of a test function. This estimate looks like the generalized stability inequality. Later on, so gave the point-wise curvature estimate like we've seen in the minimal graph. This result roughly says that if we have a two-sided stable minimal surface in a ball BR, then the norm of second fundamental form at the center of a ball can be controlled by C over R squared. For a triple junction surface, we cannot get the point-wise curvature estimate right now since there might be still a lot of work needed to do. So we will follow from the LP curvature estimate here to see if we can get some useful result. From LP curvature estimate, we can get the generalized Bernstein theorem. So Simon Yao's result says that for any stable minimal hypersurface sigma, which is complete and two-sided with n not greater than 6, and volume growth is at most CRn-1, then sigma is flat. Moreover, by the result of coding manicosis, for any two-sided orientable simply connected minimal surface, we can get sigma has quadratic area growth at most. Combining these two results, we can remove the area growth condition in the result of Simon Yao for special case n equal to 3. This result says for any two-sided complete stable minimal surface sigma, it should be flat. Now let's sketch the proof of LP curvature estimate. The key inequality in the proof is the Simons inequality. For any minimal hypersurface in Rn, not just the stable one, we have this inequality. The proof for Simons inequality is quite standard, and you can refer to some textbooks about minimal surface if you do not familiar with it. For a special case, n equal to 3, this inequality will become an identity and we call it as Simons identity. With Simons identity in hand, we are ready to give the proof of LP estimate. In the first step, we can replace phi by phi times a to the p minus 1 in stability inequality. The left-hand side is just coming from the left-hand side of stability inequality. For the right-hand side, you can expand the square term to get the 3 term here, including mixed term. In the second step, we can multiply a to the power 2p minus 4 times phi squared to Simons inequality and integrate on sigma. This term is just from left side of Simons inequality. This term here is just from this term. From this term, we need to integrate by part to get to x term here. Now, we can combine these two inequalities. Note that there are a lot of same terms in these two inequalities. We use this pen to mark the L2P terms. We mark these 3 terms as yellow. Besides that, there are 2 terms here and here, which we call the mixed term. They can be controlled by these 2 terms here by Cauchy-Schwarz inequality. No matter what, almost all of them can be cancelled out by if we assume P has this upper bound. Only L2P term and this term left. After some careful calculation, we can get this inequality here. At the last step, we can replace phi by phi p in the inequality in last step to get this inequality here. Then we can apply Holder inequality to separate these 2 terms to get this result here. By dividing this term at both sides, we can get the final result. With the help of LP curvature estimate, we can show the generalized Bernstein theorem. This theorem says that for any complete stable minimal hypersurface with area growth condition, it should be flat. The proof is quite simple, as we can just choose a test function phi in LP estimate as a cutoff function, which is stored in B2R equals to 1 in BR with a bounded gradient. Here we draw a simple figure to illustrate the choice of phi. Then we can bound L2P norm of second fundamental form in BR by these quantities. Using area growth condition, we can bound it by this term. It will converge to 0 as R goes to infinity. This tells us the curvature of sigma vanishes everywhere, so sigma should be flat to finish the proof.